Yeah, good morning. Yeah, any questions before we get started? I see that there is one person by name Arun Ramaswamy who has joined the meeting here. May I know which department he is in? Hello, Arun Ramaswamy. He is left. Okay. Okay. Let's get started. Before we go ahead, I just want to tell you that we'll have the lab class starting at 2:30 today. Okay. So we'll have an introduction to the lab class where we start the discussion on the hardware description languages, okay, and how to write code in the hardware description language for simulation of some simple digital circuits. Okay, so please join at 2:30 today afternoon for that. It will be for about an hour, right? After that, we'll tell you about the downloading of the tools and then installing it on your systems, right? And then do some quick testing of the tools for some simple circuits, right? And we'll give you the first assignment next week. First lab assignment will be given next week for. Okay. Yeah. Yeah. Any questions about what we've been discussing in the course so far? Are you able to download the lectures, recordings of the lectures? And the lecture notes, whatever I'm writing here, I will upload it at the end of one topic. That is, the current topic will be on the design of the combination logic circuits. So we may complete the discussion on this in about another 1 or 2 lectures. After that, I will put the PDF file of these notes that I'm using in the lectures. Otherwise, the recordings of lectures are available in the Google Drive. And today I have uploaded the chapters of the book also on the Google Drive. This is the book on the elements of computing systems. And it also has got one zip file, nand to Tetris. So please download that zip file. That will be required for the lab class today afternoon. Okay. Yeah. Yeah, Utkar, what is the reason? Why do you want to change it? Because the lab slot hours are 2:30 to 2 to 4. Head slot, what are the timings? I don't have the timetable here really. Two 2:30 to 3:30. Okay. If it's convenient for all others, from next week I can do it from 3:30. Okay. But today I have scheduled some other meeting at 4 o'clock, right? So we have to meet at 2:30 today. Okay. But from next week onwards, if it's convenient for all the other students also, we can meet at 3:30. Okay. Yeah. So today we'll meet at 2:30. Yeah. Okay. Any other questions? Shall we get started? Okay. Okay, so what we've been looking at so far in the course was how to come up with the expressions for a given Boolean function. First, we represent the Boolean function in the form of the truth table. From that, we get a minterm expression. Then we plot the minterm expression on the Karnaugh map. That will help us to simplify the expression so that we get the minimal expression for a given function. Then that minimal expression can be realized using the logic gates as we discussed earlier, right? So the Karnaugh map method is typically useful for simplifying the Boolean expressions for the functions with maybe 4 variables or maximum of 5 variables. Beyond 5 variables, it becomes difficult. And one can use the other method called the tabular method or the Quine mccluskey method to simplify the expressions for the Boolean functions that involve large number of variables. And as I was mentioning in the last class, one can also write the programs to implement this Quine mccluskey method, right? Where the program will take the representation of the Boolean function in the form of the min-term expression, right? And then it will do the simplification and it will give the simplified expression for that. Okay, it's out of the syllabus for this course, right? Those who are interested can refer to any textbook on the digital logic design to know about this tabular method. So if, the Karnaugh map method is kind of understood well by all of you now, we'll go to the discussion on what are called the incompletely specified functions. So far, we looked at what are known as the completely specified functions. That is, for every combination of the input variables, the value of the function is specified, right? Those functions are completely specified functions. Now we'll be seeing what are called the incompletely specified functions, where we are interested in the output of the circuit to take certain values only for certain combinations. And for other combinations, the designer of circuit does not care whether the output of the circuit will be either 0 or 1, right? And that will help us actually to come up with the expression which is simplified further, right, by making use of these combinations for which the output of the circuit is stated to be what is called the don't care. Okay, and now the Boolean function, let's say, just for an example, we consider a function of 4 variables. Let's say the minterm expression is this. There are 5 minterms in this function, but the designer of the circuit says that I do not care what will be the output of the circuit for some combinations. Let's say that's for this combination of 4 variables. If those combinations correspond to this minterm, so 10, 11, 12, 13, 14, and 15, right? Then the designer of circuit does not care whether the output of circuit is going to be 0 or 1. So D here stands for what's called the don't care term. And one commonly used application of these don't care terms in the design of digital circuits is where the input corresponds to 4 variables, and these 4 variables represent the bits of a 4-bit number for unsigned digits, unsigned decimal digits. So we are normally interested in giving the input as 0 to 9, right? And all of you know that the 4-bit combinations can give us 16 combinations, right? So we are only interested in specifying what will be the values of the output of the function for some values of this unsigned decimal digit. And for the combinations beyond the value of 9, right, we don't care what the output of the function is, right? And we'll see that it will help us get a simpler expression than the case where we don't use the don't care terms. Okay, suppose we don't use the don't care terms here. What is the expression that you will get for this function f here? All of you can do this exercise. right? So just take only the min-term expression. Right? So the min-term expression is containing 2, 3, 2, 3, 4, 5, and 7. Right? And if you apply the Carnot-Maper simplification method, we can identify the prime implicants, and then we can identify the essential prime implicants, right? So if you start identifying the prime implicants, we can see that all of these are prime implicants, right? And then we can start marking the essential prime implicates. So this is an essential prime implicant because the min-term 2 is covered by only this prime implicant, and this is also an essential prime implicant, right? And we can get the minimal expression for this without using the don't care terms, right? As the two essential prime implicants, that is w bar x bar and then y plus w bar x then y bar, right? And then we have this min-term, that is min-term 7, which is covered by two prime implicants, and one can choose any one of them, right, to come up with the minimal cover, right? Let's say I choose the w bar y j. That corresponds to the combination of 3 and 7, right? I mean m3 and m7, right? So this is the minimal expression for this function when I don't make use of the don't care terms. Now let's see what happens when we make use of the don't care terms, right? So I'll draw the Carnot map again. So we have to mark all the ones that we had earlier, right? Now let's mark all the don't care terms as D. Now we can see that the don't care terms are 10, 1. Yeah, we'll write D here. Sorry, D here, 10, 11, then 12, 13, 14, and 15, right? And we'll follow in the same manner as that we have done earlier. But only thing is we'll form the prime implicants and essential prime implicants, but we don't to bother about covering the don't care terms, all of them, right? But we have to make sure that every one is covered by the prime implicants that are required, right? So now let's identify what are all the prime implicants. Now the prime implicants can be formed, right, by groups of ones only or groups of ones along with the don't care terms, right? So now we can see that the prime implicants will be completely different here now, right? So this will be one prime implicant, right? So basically we'll assume that we'll take an advantage that the don't care terms can take any value. So we'll assume that all these D values will become 1 for the combinations, right? And we'll try to make use of that. And then we see that we get here larger groups of ones, right? Okay, so now these are all the prime implicants. Now we can see that there is a there is a don't care term here in the cell corresponding to 1110, and we are not bothering about covering that don't care term because it's not combined with any one in a group of ones and D's here, right? So that's why any prime implicant that's formed should have at least a single one, right? And it can have more than one single one also, and it can include some don't care terms as well, right? So now let's identify what are all the essential prime implicants out of this, right? So still this is an essential prime implicant, right? Because this term 2 is covered only by this prime implicant, right? And this is also an essential prime implicant, right? And then we have this M7 that can be covered by any one of the two prime implicants. So now what is the expression, right? Now we see that the F is going to be having these two essential prime implicants, right? And this group of 4 ones, right? In the cells 4, 5, then 12 and 13 will give us X, Y complement, right? So this is XY complement, right? And then the other essential prime implicant is, we can verify that it is X complement Y, right? Now, in order to cover this min term, we can choose any one of these two prime implicants. Let's say I choose YZ, right? So what is it we see from the two expressions? The earlier one is where we don't make use of don't care terms, and we see that there are 3 product terms, and each of these product terms has got the 3 variables. Whereas when we use the don't care terms, right, basically in this case, it so happens that, right, the number of product terms does not change, but the number of variables in each of the product terms reduces by 1, right? And as far as the combinations corresponding to the min terms are concerned, the output of circuit is going to be 1, right? And for the don't care terms, right, we cannot say what will be the output of the function. It can be either 0 or 1, right? And for all other combinations, right, where we don't have either 1 or the D, right, it will be an output of 0. Okay. And so basically what it says is that by using don't care terms, right, we realize the required function for the combinations where the output is specified as 0 or 1, right? For the combinations which are not specified, right, the circuit may give either 0 or 1, right, depending on what is the expression that is finally realized. And typically it will lead to a simpler expression than the case without using the don't care terms. Okay. Yeah. Any questions about this? I'll give you one more exercise for practice, right? But I just want you to understand what is the don't care term and how the don't care terms can be used in this simplification of the expressions. The method is similar to what we had done earlier, where we had only the min terms, right? But the only change is that the min cover is going to include, or the minimal cover is going to include all the essential prime implicants plus prime implicants that are required to cover only the ones, right? And we don't have to bother about covering all the D terms. Okay. Okay, let's do a small exercise for practice. Suppose I give you a function which contains these min terms. One, 4, 5, 13, 14, and 15. Then the design of the circuit says that, right, I don't care what is output of the circuit for the combinations corresponding to 6, 8, 9, and 12. Okay. So I want you to come up with the simplified expression without having the don't care terms. Then the simplified expression where the don't care terms are also taken into consideration. Yeah. Please take a couple of minutes to do this exercise and tell me, right, what is the expression for each of the cases. So I given here with the corner maps, one without the don't get terms and the one with the don't get terms included, right? So come up with the prime implicants and the essential prime implicants. We say that there are several prime implicates, and we can identify the essential prime implicants out of this. So if we don't use the don't get terms, you can verify that you will get W complement X Y complement, W complement A complement Z, right? Then Wx Y. So these are the three essential prime implicates, and we are left out with one main term that's not covered by these three essential prime implicates, that is the 13. So 13 can be covered by any one of the two prime implicates, right? And one can use, let's say, X Y complement Z. So this is the minterm. Sorry, this is the minimal expression that you would get if you don't use the don't get terms. So let's see what is it we'll get if I use the don't get terms. So this group of 4 that includes 3 ones and 1 D can be combined, right? Yeah. Then I can have this. Sorry, I think I marked something wrong here. Let me just check. 6, 8, 9. So this is not correct. It should have been 12, right? So now we see that so these are the prime implicants that we'll have, right? And we don't have to worry about covering the D terms which are not covered by these prime implicants, right? And we can easily verify that all these three are essential prime implicants, right? So you can verify that the Boolean expression for this is XY complement, right? Yeah, XY complement plus Y complement Z plus X Z complement. I'm sorry, it should be just 1 minute. Yeah. Actually, there are two prime implicants that can be pushed here, right? So there are only two essential prime implicants, right? One for this, right? And the other one is this. Sorry. Right? So this prime implicant is, sorry, this essential prime implicant is Y complement Z, whereas this is Wx. So if we include those two essential prime implicants, we'll get Y complement Z plus Wx, right? Then we are left out with this minterm 4, right, which is covered by two prime implicants. One can choose any one of them, right? So if I choose, let's say, this prime implicant, right, so that will give us X, right. right? So now we can see that when you use the don't care terms, right, the number of product terms is reduced by 1, right? And of course, the number of variables in each of the product terms also is reduced by 1, right? And typically, when we use such circuits multiple times, right, these savings can be significant, right? And that will help us to come up with the circuits which are less complex. Okay, so we try to come up with the minimal expressions that exploit the presence of the don't care terms, right? And typically that will lead to a simpler expression, either in reducing the number of product terms or reduce the number of variables in each of the product terms. Yeah, any questions about this? Okay, I'll just give you one more exercise for practice. I'll not do it here now, right? You can try it out later and then check the solution. Yeah, so please take it as a home exercise for you to do this problem, right? So again, get the minimal expression for the case where only min terms are considered, and again get the minimal expression where the don't care terms are also taken into consideration. Yeah. So any questions about what we have discussed so far? I just want to pause a little bit. Yeah. Oh, is there some problem? Okay, I think. Okay. So what is the significance of don't care terms? As I said, there are certain combinations of the inputs where the designer of circuit does not care what the output of the function is going to be, or what the output of circuit is going to be, right? And we make use of these combinations to come up with the simpler expressions, right? As we are showing through a few examples, right? When we use the don't care terms, right, then typically we get a simpler expression than the case where the don't care terms are not used, right? And as we go along, we'll be seeing a few practical circuits, right, where the presence of don't care terms will help us to come up with the much simplified expressions for the functions that we want to realize using the circuits. Okay. Yeah. Any questions? Yeah, these are 2 questions I see in the chat box. Okay. So let's move on. So all of you must be now familiar with how to come up with the minimal expression for any Boolean function whose description is given in the form of the truth table or in the form of the midterm expression, right? That may include the midterms as well as the don't care terms. Now, if you look at the final minimal expression that we get, right, they are of the form of called the minimal sum of products form, shortly called as the MSO, right? And once we get the minimal sum of products form for any Boolean function, right, the realization of circuit in terms of the logic gates is a very straightforward process, right? So what all we need to do is use an AND gate for every product term, and then the outputs of all the AND gates correspond to the product terms in the expression will be combined using one OR gate, right? And that will give you the circuit for the given function. So let's take the latest example that we have, right? Where by using the don't care terms, we come up with this minimal sum of products, right? F equal to y complement z plus wx plus x y complement, right? Now, assuming that we have both the normal form and the complement form of each of the variables available to us, right? What all we need to do is use one AND gate for each of the terms here, each of the product terms, right? So the first AND gate will take the y complement, then z, right? Then the second AND gate will take w, x, right? The third one will take x, y complement. And then the outputs of all these AND gates are given as input to the OR gate. And the output of this OR gate will be the F. Right? And whenever we give the particular combination of these variables w, x, y, and z, right? Either they're taking zeros or ones, right? Then for all the entries of the truth table where the minterms are present, right? Then those combinations, the F will be 1, right? And for the entries where there are no ones, right? And which are also don't care terms, right? Then the output of the circuit will be 0, right? And for the combinations corresponding to the don't care terms, the F value can be either 0 or 1, right? And we now don't bother about this don't care term combinations. We only bother about the minterm combinations and the other combinations where the output of circuit is expected to be zeros, right? And this circuit will give us the corresponding outputs for those combinations. Okay. Now I just want you to understand the delay involved in generation of the output after we present the inputs. Let's say we give all the inputs here, that is the W, X, Y, and Z, and also their complements at time t equal to 0, right? What you want to know is at what time the output F will be valid, right? Let's say if I give any of the combinations correspond to this minterms like 1, 3, 4, 7, or 11, right? When will the output of this circuit will change to 1, right? And that time taken will be dependent on how many gates these inputs have to pass through, right, before the F takes the corresponding value. So we see that this is a 2-level logic circuit. What is the first level here? It will consist of several AND gates, right? And the level 2 is typically only one OR gate, right? And typically we specify the delay in generation of the output for a particular gate after the inputs are available as what is called the propagation delay of the gate. And we denote that by a symbol tau, right? And we'll be using this entity called tau extensively in our later discussions, right? So what does this tau indicate, right? It tells what is the amount of time the gate will take to generate the output, right, after all the inputs are available. Okay. And the typical value of this tau will change from time to time, depending on the technology that's being used to build the gates, right? And typically nowadays it's of the order of a few picoseconds, right? I think all of you are familiar with the units like seconds, then milliseconds, microseconds, and the nanoseconds, right? As all of you know, the nanosecond is 10⁻⁹ second, right? And I think all of you might also be knowing that the picosecond stands for 10⁻⁻12th of a second, right? We may think that why are we bothered about such a small value of the time, right? As we'll be seeing later when we build complex circuits, right? The delay of the circuits is going to be several orders of this tau, right? And then we have to worry about the total time that's taken by the circuit, right? And also, I think just to give an idea why we are really bothered about this, right? So typically when we consider the current day process, all of you must be knowing that, right? Typically this process run at some clock speeds, right? And most of the process nowadays run at either 1 gigahertz or higher clock rates. Let's say we're talking about the process running at 1 gigahertz, that is 10 power 9 cycles per second. One cycle time is 10 power minus 9 seconds, that is 1 nanosecond. And typically in the current day process, when you study the computer science course, you will understand that fully, right? We expect that every instruction that we are trying to execute must be completed, and the main operation of that instruction should be completed within this clock cycle period. That is, the operation must be completed within 1 nanosecond time. Okay. Now, the circuits that we are going to build later, we'll be seeing that we'll be building arithmetic circuits to perform the arithmetic operations for the integer type data or for the floating point type data, right? So we'll be interested to know whether each of these operations can be completed within this 1 clock cycle period, right? And in order to see whether the operation can be completed within that 1 clock cycle period, we need to know what is the delay of the arithmetic circuit, right? And as we'll be seeing later, the arithmetic circuits are all going to be built using these logic gates, right? And it will not be a simple 2-level logic gate circuit, right? But it may be several levels of logic gate circuits, right? Then we'll be interested in what is the time that the circuit will take to generate the result once the operands to the arithmetic circuits are made available, right? And that's where this tau will be playing a very crucial role, right? And the value this tau takes, right, will finally decide how much time the arithmetic circuit will take to perform the operations. As we'll be seeing later, right, each of the types of arithmetic operations that we are interested in will be carried out by a different circuit, and the complexity of circuit will be determining the amount of time the circuit will take, right? And all of that will be dependent on this value of tau. And from now onwards, we'll be specifying the delay of any circuit in terms of this tau. Okay. So if you have a simple expressions like what we have been looking at, and if the simple expressions can be represented by the 2-level logic gate circuits, right? We see that the first level of circuit here, that is AND gates, will take 1 tau, right? And the second level logic circuit will take another tau, right? So the F will be taking the valid value, right, at the time t equal to 2 tau, right? So if you have any circuit that can be realized as a 2-level logic gate circuit, the delay of that circuit is going to be 2 tau. And let's say if the tau value is of, let's say 10 picoseconds, just for the sake of discussion, right? Then the delay of the circuit is going to be 20 picoseconds, right? And as we'll be seeing later, whenever we discuss the design of the arithmetic circuits, for every circuit, we'll be interested in what will be the delay of the circuit expressed in terms of this propagation delays of the gates, that is tau. Okay, yeah. Any questions? Yeah. Okay. The question is, why is the delay of the NOT gate not counted? As I said, we normally assume that the variables and their complement forms will be available as we'll be seeing later in the course, right? We'll be using what are called the flip-flop circuits, right? And the output of the flip-flop will have both the normal form of the variable and also the complementary form of the variable available, right? And we don't consider the delay in the complement operation, right, in the computation of the delay of the overall circuit, right? And if it is the case that the complement form of the variables is not available, right, then the delay of the NOT gate also has to be taken into consideration. Yeah. Also, won't it be 3-level as R would take only 2 inputs at once? No, we never made that statement. Actually, if you remember in one of the earlier classes, we said that there is what is called a fan-in parameter of a gate, right? That fan-in parameter will tell us what is the maximum number of inputs a gate can take, right? So right now we are assuming that the OR gate in the second level of the logic circuit will have the number of inputs that is below or less than or equal to the fan-in parameter. If the number of inputs to the OR gate, that is, if the number of product terms in the expression exceeds that fan-in value, right, then I have to use one more level of OR gate. Okay. Just for the sake of discussion, right? Let me go back to the notes here. So right now, this OR gate takes 3 inputs, right? So we're assuming that the fan-in is greater than 3, right? Suppose we had a logic gate's Boolean expression where there are, let's say in this case, right, there are 4 product terms. And if I'm going to use an OR gate with only a fan-in of 3, right, then all the product terms will be generated after 1 tau. Then we'll give the first 3 product term outputs as input to one OR gate, and the output of that OR gate will go to another OR gate where this another OR gate will take this last term Wx, right? Then it will be a 3-level logic gate circuit, right? Then the delay will be 3 tau, right? And it all depends on what is the fan-in parameter of the technology that's used for the building of the gates, right? And if the number of product terms in your minimal expression is exceeding that fan-in value, right, then the delay of the circuit is going to be 3 tau and not only 2 tau. And as you go for larger number of variables, the number of variables that will go as input to the AND gates can also increase. Again, the fan-in parameter will come into the picture, right? And if the number of input variables is much larger than the fan-in value, therefore, the number of variables that are present in each of these product terms in the final minimal sum of products is exceeding that fan-in limit, right? Then for every product term where the number of input variables is more than the fan-in value, then we have to use 2 levels of AND gates, right, to combine the input variables, right? Then in that case also the number of variables, the number of levels of the logic gate circuit will be more than 2, and accordingly the delay will be more, right? But typically, as we'll be seeing later, right, we will not be dealing with the cases where the number of input variables is more than 4 or 5, which is typically the fan-in value of the gates that are currently being used. Okay, yeah. Okay. Now we'll be discussing a very interesting thing where we see that in the current implementation of the circuit using the gates, we have used the first level with the AND gates and second level with the OR gates, right? And we can show that we can use a single type of gate, let's say in this case the NAND gate, right, to release the whole circuit, right, by using only one type of gate, that is the NAND gate, right? So let's say I take this expression we have here, f equal to y complement z plus wx plus xy complement. So can we write this as the double complement of all of this? Right? And then let's take the inner expression. Let's leave out the outer complement as it is. Can you apply the De Morgan's law for this? What does the De Morgan law say? Right? I hope you remember that, right? If I have a NOR operation on the product terms, right, the De Morgan's law say that it's equivalent to, yeah, maybe if you people don't remember, right, let me go back notes. Let me just see. Yeah, we have here, right? What does the De Morgan's law say here? A x plus y complement will be equal to x complement y complement, right? So we'll be making use of this De Morgan's law to come up with a different form of the expression. So we see that this involves a complement operation on the OR of 3 terms, right? So it will be complement of each of the terms. Right? Now we see that this can be realized using one NAND gate. Right? This can be realized using another NAND gate. This can be realized using another NAND gate. Now whole of this can be realized using another NAND gate. Right? So the circuit that we had drawn earlier can be simply redrawn by replacing every gate that's present there We'll put the arrow marks to simplify it. Right? So if you really look at it, what all we have done is every gate that's present in this two-level logic gate circuit with the AND and OR gates, right? We simply replaced each of them by the corresponding NAND gates, right? The inputs are exactly the same as what it was there in the previous diagram, right? And we get a circuit with only NAND gates, right? So this gives us to build the circuits with only one type of gate, again from the fabrication point of view, right? When we manufacture the chip, right? Normally it will be helpful to use only one type of gate, right? And what you see here is that one can come up with the two-level logic gate circuit first with the AND and OR gates, right? And then we simply replace the AND and OR gates with the NAND gates, right? And we get exactly the same functionality of the circuit. And that can be verified by applying the De Morgan's law for the given function, right? And what you are getting is the AND OR expression, right, will be equivalently expressed in terms of only the NAND operations, right? And one can realize the complete circuit using only the NAND gates, right? But one has to be careful when you are dealing with the expressions with product terms where there is only a single variable, right? Let's say, just for sake of discussion, right? In this case, I have only So here I have the first term as only y, right? So what will be the application of the double complement on this will be, right? So we'll take the inner complement operation here, then apply the De Morgan's law. Right? So we see that now this will be represented. Sorry. This will be represented by using one NAND gate. This will be represented by using another NAND gate, right? Then the whole of this will be represented by using another NAND gate. But what is the input to this second level NAND gate? It is not y, it should be y complement, right? And that should not be forgotten, right? So now we are going to have a two-level NAND gate circuit with two NAND gates in the first level and one NAND gate in the second level. And this y complement will be given as input directly to the second level NAND gate. So when we are dealing with the expressions with only product terms having a single variable, right, it has to be noted that those variables have to be complemented before they passed on to the second level NAND gate. Okay. Otherwise, the method is very simple, right? First, come up with the minimal sum of product expression, then realize that using the AND OR gate circuit, and then replace each of the AND gates and the OR gates with the corresponding NAND gates, right? And that will give you a circuit with only NAND gates, right? And that can be used to realize the function that's required. And if there are the product terms with only single variable in that, it has to remember that those terms have to be complemented before they are given as input to the second level NAND gate. Okay, so this is normally done, right, so that we get circuits with only one type of gate, right, called the NAND gate. And this is the reason why we call this NAND gate as the universal gate, because any circuit for which we can come up with the truth table, which can be simplified, and then we get the minimal sum of products. And once we get the AND OR gate circuit for that, we can replace all the AND and OR gates with the corresponding NAND gates, right? And therefore, we can realize any Boolean function using only these NAND gates, right? And therefore, this NAND gate is also called the universal gate. And most of practical circuits will go for this kind of a method where only one type of gate is used in the design of the circuits. Okay, yeah. Any questions? Yeah, just let me just check. There are any questions here? Yeah, there are a couple of questions here. Will tau be the same independent of the number of inputs? Typically, the tau be the same, right? As long as the number of inputs is less than the fan-in parameter. Yeah. The second question is, in the last circuit, the second level NAND gates input would not be in sync. Yeah. Finally, when is the time? What is the time at which the output will be valid? Output will be available. It's still 2 tau, right? Yeah. Yeah, one of the inputs is available earlier. That is that Y complement input will be available to the second gate earlier, right, at time t equals 0 itself. And the outputs of the first level NAND gates will be available after 1 tau, right? But we know that it's a 2-level logic gate circuit, so we'll wait till 2 tau to take the output of the circuit and then use that, right? And as we'll be seeing later, right, there will be several such cases, and that's why we have to determine what is the delay of the circuit, and that after the delay of circuit, the valid output of the circuit will be guaranteed. Yeah. Just 1 minute. Yeah. Okay. Yes, that's correct. The input frequency must be at the max inverse of the total delay of the circuit. I mean, right now I'll say yes, right? But at a later point, we'll be seeing how to deal with the circuits which are very complex, right? And we cannot force the clock period to be the inverse of the total delay of the most complex circuit, right? So, I mean, this we might wait till the next course, that's computer organization architecture course, right? And most of the operations we'll try to complete in one clock cycle, but there will be a few complex operations, right, that will require more than one clock cycle. And those operations will be identified. Then the processor control circuit will know that when this operation is going to be carried out, it will take multiple clock cycles to complete the operation. Yeah. Because if you put the input frequency as the maximum inverse of total delay of circuit, right, that's going to be very, very inefficient. Okay, because not all the operations will take that kind of a delay, right? So we don't want to waste the time. Yeah. Okay, good. Any other questions? Okay, I think maybe let me stop at this point, right? So we'll meet at 2:30 today, right, for the lab class. So we'll start the discussions on the hardware description languages and how to write the code for some simple circuits, right? I will leave the details of the downloading of the tools and installation of the tools, and then how to make use of the tools. You can go through the help material that's available, right? And then try to download the tools and install them on your laptops, right? We'll only look at the hardware description language and how one can write the code to synthesize some simple circuits, so that you will be in a position to start with the first lab exercise in the next week. Okay? Yeah. Yeah. If there are no other questions, so then we'll close this session. Okay. Okay, thank you then. Bye. See you later. Yeah, I will upload these notes.